At some point in time in your studies of engineering, especially mechanical engineering, you will come across this concept known as torque. Now, torque is a force that tends to cause some sort of rotation, and torsion in this case is that twisting of an object due to some form of applied torque. Now, we're going to analyze the concept of torque using this question here, where we need to find the maximum shear stress as a result of applied torque. And we're going to also aim at finding something known as the angle of twist. So let's begin and let's see how interesting this topic really is. Now, to make things even more interesting, we're going to say that this end that I'm sketching these hashed lines on, that's going to be a fixed end. So as you can imagine, when torque is applied to this free end right there, it's going to cause some form of twisting to take place in the entire system. And this very prominent white line that we have right there, that's our reference. Let's say that's our neutral point or our neutral axis. And as twisting starts to take place, the material is going to somewhat change in terms of that axis. And I'm sketching right there where that line would probably, let's assume it's going to probably twist to some degree. And the angle between our new reference point and the angle right here between our original reference line there and the new one that I've drawn in that happened as a result of the applied torque, that's known as our angle of twist. And what we're going to try and understand here is what happens when we have, let's say, a drive shaft, because that's quite a common setup. So we have a drive shaft and the torque that is applied is 1200 Newton meters. Its length is 0.7 meters and we have a diameter of 50 mil. We also know its modulus of rigidity, it's steel, so we're using 90 gigapascal. So the starting point that I would always tend to advise is to set out the torsional equation. So this here is our torsional equation, and it's T for torque, J for polar second moment of area, and I'll talk to you what each of these represents, G for modulus of rigidity, theta, angle of twist, that capital L is for the length of the shaft in this case, tau for shear stress, and R for radius. So for this question, what I am going to advise here is this equation. It's quite a dynamic equation in that we have several variables and it's a three-part equation. So therefore, we have to look at what we want to find and then figure out which one of the other, let's say, fractions then or ratios consist of the other two. So let me show you what I mean. So let's say we're going to calculate the maximum shear stress. Now this is our maximum shear stress. Pointing the purple arrow at our tau symbol. That's our maximum shear stress, and that happened as a result of some form of applied torque. Now, in order to use the maximum shear stress, we would have to know what our radius is, and we do because we have the diameter. So what we need to do then is to look at the other two parts of the equation and see which one of those parts we have both of those variables for. So we know what torque is. So torque is given as 1200 Newton meters. And we have that J for polar second moment of area. And what J represents, it represents the system's resistance to twist. So J, it's a geometric property and it's based off of the area that we have. And there are various formulas that we can use to find J. But if it is that we have a circle, like the one that we have, or a circular shape like the one that we have there, then J is equal to pi d to the power 4 over 32. And remember, J represents a geometric property, so it depends on the shape that we have that dictates what this formula is. So now that we have this formula for J, we can go ahead and work out what J is and then use the chunk of the equation that we need. So let's work out what J is then. 0.05 to the power of 4 and all divided by 32. So we get J as 6.136 and times 10 to the negative 7, and the unit for J is meters to the 4th power. So that gives us J. So now the next bit that we are going to look at is how to set out the next part of the equation that we have here. So we know that we're going to use shear stress divided by radius. That will be equal to this chunk of the equation only, because we have what torque is and we've just calculated J. So therefore, if we were to now make tau the subject, then that would be equal to torque multiplied by radius and all divided by J. So you can see where this is going. It's just a matter of substituting those values now. So let's go ahead, substitute those values and see what we get. So that's our shear stress equals torque, which is 1200 Newton meters, multiplied by our radius would then be 0.025, half of our diameter, and all divided by the J value that we just got, which is 6.136 times 10 to the negative 7. So our maximum shear stress then is going to be 48.89, and this would be times 10 to the power of 6 pascals, but we can just write it as megapascals. So that represents our maximum shear stress. Now, to get the angle of twist, we're going to go back to our formula. So I'm just going to write it down for us to reference. So that's our formula, the same one that we've just had. So our angle of twist is right here. And we have all of those variables that's needed for our angle of twist. We have modulus of rigidity that's given to us, that's 90 gigapascals. And we also have the length of the shaft, which is represented by our capital L there, which was 0.7. So what we need to do then is to determine if we're going to use this chunk of the equation or this chunk to pair with that bit that we have there. And in this case, we can actually use either of them, because for here, the first part, we have torque and we have the J value. We also just calculated our shear stress and we have what radius is. So it really doesn't matter which one of these side of equation we pair with. So I'm just going to use, for simplicity, the left side. So I'll rearrange that to get torque multiplied by length over J times by G. So that's just rearranging the entire equation to make the angle of twist now the subject of the formula. So this will be 1200 for torque multiplied by 0.7 for our length, multiplied by our J value that we calculated previously, 6.136, and times 10 to the negative 7, and that will also be multiplied by our 90 gigapascal, which is 90 times 10 to the power of 9. And when we put all of that in, our angle of twist turns out to be, in radians, 0.0152, and this is radians. So if we want to convert then from radians into degrees, so all we have to do here to convert into degrees is just 0.0152 and multiplied by 180 over pi. and this will give us a small degree of 0.87 degrees, which is quite small, and that's what we expect because our material, it's got relatively good properties, so we wouldn't expect to have any massive twist. Now, if you like this type of content, if you would like me to go further into more analysis of torque, torsion, then please let me know in the comment, because I would really love to go deeper into this topic, but only if it's beneficial to you. Once I have your response, you will see the next video right here in the top right corner. And until then, I will see you in the next video.